Okay, in chemical bonding, there are some exceptions to the octet rule. Not all the elements are going to get 8 valence electrons. Sometimes they have less than 8, like hydrogen. Sometimes they have more than 8. Boron has less ability to attract electrons to fill its octet, as it only has 5 protons. So boron would be an exception to the octet. It has less than 8. Right here, it only has 6. Expanded octets, atoms in periods 3 through 7, which means the third energy level through the seventh energy level, can bond with other atoms in such a way that they end up with more than 8 electrons in their octet. So this would be greater than 8. They're able to do this because they have empty d sublevels that they can fill. So if you'll notice, phosphorus here is 3s2, 3p3. Well, there's a 3d sublevel that has orbitals that electrons can enter. Some of the electrons are promoted to the 3d sublevel, and that's why it's allowed to have another bond here. So this would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 valence electrons. Sulfur is 3s2, 3p4. It also has a 3d sublevel that some electrons can enter into, and therefore it's allowed to have a violation of the octet rule, more than 8. Xenon as well. Xenon is a noble gas that actually bonds with fluorine. Some of its electrons are promoted to the 5d sublevel in order to do this. Formal charge. In some cases, the atoms in a molecule can be assembled in different ways when drawing a Lewis diagram. Sometimes there's different ways to draw things. Formal charges are calculated to identify which is the most stable structure. The sum of the formal charges on each atom will be 0 for a neutral molecule. The sum of the formal charges on each atom will be equal to an overall charge if it's a polyatomic ion. How do you tell which one is more the stable function? Based on formal charge, the more likely the Lewis structure will have formal charges that are closer to equal to 0. If there are negative formal charges, they should reside on the more electronegative element in the structure. For example, well, how do you calculate formal charge? Formal charge is equal to the number of valence electrons assigned to the neutral atom minus the number of electrons assigned to the atom in the structure, or what I like to call the number of electrons touching it. I'll show you that in just a second. This number is also equal to the number of lone electrons around the atom plus the number of bonding electrons divided by 2. So, which is most likely the structure for NCl3? This one or this one? Cl and N both have an electronegativity value of 3, so how do I know which one goes in the middle? That's what we're trying to figure out. Well, according to this, the valence electrons, nitrogen is supposed to have 5 valence electrons and chlorine is supposed to have 7. What do I see up here for nitrogen? I see 1, 2, 3, 4, 5, 6, 7 that are touching nitrogen. Chlorine, I see 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This chlorine, I see 1, 2, 3, 4, 5. So you take this minus this, and you get a negative 2 here, 0, 0, positive 2 here. This structure is not likely to occur because I don't have zeros here and here. This one, chlorine is supposed to have 7, 7, 7. Nitrogen is supposed to have 5. How many do I see here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Nitrogen, I see 1, 2, 3, 4, and 5. So this is the correct drawing of NCl3. Let's try this one. Which is the most likely structure for SCN-1? This one or this one? Sulfur and carbon both have electronegativities of 2.5, so we don't know which one goes in the middle. Well, carbon's supposed to have 4, sulfur is supposed to have 6, nitrogen is supposed to have 5. Okay, I see right here 1, 2, 3, 4, 5, 6 for carbon. I see 1, 2, 3, 4 for sulfur, and I see 1, 2, 3, 4, 5, 6 for nitrogen. So these numbers are fairly large. I doubt this is the one that is correct. If I look at this one, carbon once again is supposed to have 4, sulfur 6, nitrogen 5. Sulfur, I see 1, 2, 3, 4, 5, 6. Carbon, I see 1, 2, 3, 4. Nitrogen I see 1, 2, 3, 4, 5, 6. Now, when I do this, I do end up with a -1 charge for nitrogen. Nitrogen is the most electronegative element, and I should have an overall charge of -1. Bond energy. The amount of energy that is required to break the bond between two specific atoms in a molecule is called bond energy. Likewise, the amount of energy that is released when a bond is formed between two specific atoms is the complete opposite. For example, if I want to break this bond right here, it's going to require a certain amount of energy, that bond energy, to break that bond. Okay? It would be endothermic. Likewise, if hydrogen and chlorine get together to form a bond, that means it's going to release energy. So it requires energy to break a bond. Energy is released when a bond is formed. As the number of bonds between two atoms increases, the bond length decreases and the bond energy increases. A single bond will have the longest bond length. A double bond will have shorter bond length, and a triple bond will have the shortest bond length. It's also the strongest bond, therefore it requires the most bond energy. This one will require the least amount of bond energy. So fluorine has single bonds, oxygen has double bonds, nitrogen has triple bonds. So this one would be the longest bond length. This one would be the shortest bond length, measured in nanometers. This one would require the least amount of energy to break. This one would require the most amount of energy to break. As the atomic radii of bonding atoms increases, the bond length also increases, and the bond energy therefore decreases. A closer proximity to the shared electrons allows for a stronger force of attraction between the protons and bonding electrons. What does that mean? Chlorine, bromine, and iodine. As you go down, they become bigger atoms. Obviously, iodine's really big. Chlorine is a little bit smaller. So since they're smaller, the distance between the nucleus of carbon and chlorine is less. So this is a smaller bond. Here's the bond length. This is a larger bond length. This is the largest bond length. And because this is the largest bond length, it requires the least amount of energy to break. Resonating structures. You might have heard of these last year. For many molecules, there are double or triple bonds included between different atoms. This results in two or more possible ways to draw the double or triple bond. For example, this is ozone. I have a double bond right here. Could I have put the double bond on this oxygen? Yes, like over here. Okay? In actuality, that's exactly what's happening. It's over here, then it's over here. It's over here, then it's over here. And it just constantly resonates back and forth at a very high speed. So both bonds are in the same length, as they each contain 3 electrons. Ozone is actually the average of these two structures, so we call that a bond order of 1.5. Okay? Sometimes it's double bond, sometimes it's single bond, sometimes its bond order is 2, sometimes its bond order is 1. Average them, what do you get? 1.5. Nitrate, could I have put the double bond here or here? Yes and yes, and therefore there's 3 resonating structures for nitrate. Okay, so the bond order for this would be, well, 1/3 of the time it's double, 2/3 of the time it's single, so we call its bond order 1.33. Formate, I could put the double bond here, 2 resonating structures. Bond order would be 1.5. Which structure has the shortest bonds? Well, this is going to have 2 resonating structures. I could put the double bond here or here, so its bond order would be 1.5. This one, I could put the double bond here or here, so its bond order would be 1.3. Therefore, this would have the longer bond because it's only 1/3 of the time that it's a double bond. This is 1/2 of the time that it's a double bond.